Welcome to the operations research course. So continue with our topical issues in operations research. We will look at the technique of simulation. What do we refer to as simulation? So in this lecture or in this lecture series, I will divide it into two. So the first series will look at introducing as to what simulation is, the type of simulation models, the simulation process, how we go through the simulation process, or how most softwares are developed through the simulation process. Then we'll look at how risks are assessed using a stochastic simulation. So we'll use the Monte Carlo sampling process to develop a stochastic simulation algorithm to see how we can simulate some activities. So simulate a typical queuing system in a mining environment. Then we'll also look at how random variates are generated. So there are several methods or techniques that are used. Then the second phase of the lecture, we'll look at how we generate random variates using probability density functions, how we determine the distribution of the various random variables, and how a goodness of fit can be tested, and also how we can analyze some simulation outputs and some few simulation languages that are available on the market. So let's see what we mean by simulation. So usually when we talk about simulation actually refers to the process of designing a model of a real world system, and it's used to conduct experiments, right, on the models. So for the purpose of understanding how the system work or how a system can be evaluated, using several strategies. So simulation is one of the most widely used um, operations research technique. It has found very wide application in the mining and allied industries. So what is a system? As we are looking at modeling a particular system or simulating a system or trying to understand the behavior of a particular system. So a system is actually a group or collection of interrelated elements, that work together or that cooperate or that have some relationships to accomplish some stated objectives, right? So usually a model is generated or is produced to represent a particular group of objects or ideas in some form other than that of the entity itself, right? So a model is a representation of a group of objects or ideas in a form other than the entity itself, right? So models are very important when we want to understudy a particular system, in the real world, because if we cannot destroy a system in it entirely, or we cannot recreate a system in it entirely, then it means that we need a model to represent that system so that we can work our way on that model, and see how the model reacts or affects, or how external factors affect the model. So models are very important when we are dealing with simulation techniques. So the simulation models, are classified in different ways, right? So we can classify several simulation models. We can see them as symbolic simulation models, or what we refer to as iconic. Then we are familiar with deterministic or stochastic simulation models, right? And we have a static or dynamic simulation models, discrete, continuous, or combined, either discrete or both discrete and continuous all working together called the combined simulation model. So we'll take them one by one and we'll just understand these names. So when we talk about symbolic simulation models, right, we are looking at models that are physical in nature and they represent the real systems, and mostly they are iconic, and primarily they are used for training purposes. Like for instance, we have the driver simulators, we have the flight simulators, we have um, machine simulators, and they are used to teach operators, how to operate the machine, if in the form of a plane. Then we have the flight simulator, how to, teach a pilot how to fly a particular plane, different kinds of planes, how they behave aerodynamically, how to handle emergencies, right? And in a typical mine, we can also use the operators, let's say the simulators for excavators, track simulators, even sometimes shafts, shaft driving, the lowering or up or lifting skips or cages in a particular shaft in an underground mine, they are all simulators. Or even we want to look at how to fly a particular drone for area survey. We could learn it on the simulator before we go to the field. So all these are forms of what we call symbolic or iconic simulation models, right? So they are those in which the properties and the characteristics of the real systems are represented in mathematical or symbolic form, right? Symbolic form. And sometimes we can represent them mathematically, right? Or using a lot of mathematical symbols. And the symbolic models are usually run on a computer, right? They are usually run on a computer. So normally the computer experts will say that we have some source codes that are running all these icons, right? All these icons, all these models. So that's why we say they are like mathematical, or they are represented in a symbolic form, so that to control that form of icons or the physical representation of the model, right? Good. So we normally run them using computers, and therefore, if you have a very big simulator, then it means that you need a very big or high capacity computers, where these days they are looking at supercomputers, right? Then there is this aspect of deterministic or stochastic simulation models. So deterministic models, or usually when the simulation um, is related with random variations in the system, right? Or random variables, then we say that they are either deterministic or they are stochastic, right? So when we say deterministic, it usually refers to the randomness, the ignorance of randomness, or we don't actually see randomness. There is some certainty in our values or in the outputs, right? Or in the system. So deterministic just gives one particular value, let's put it that way, by one particular result or answer, right? You need to modify the entire system or one parameter, then you get one value, right? However, the stochastic looks at randomness in the system, right? Randomness of the components in the particular system. So we are able to get a range of values that correspond to the model, or a range of values that are used to get more understanding in the system. So we have a deterministic and we have the stochastic. That's why we normally say that the stochastic are used for risk evaluation, right? Then we have the static or the dynamic simulation. So when we talk of the static, then we are referring to time, dynamic, static, they all relate to time. So if you model something and you relate it with time, the the system is at a single point, right? It's static. Then we like it's immovable. Then we say that it is a static simulation model, right? Static simulation model. For instance, a cash flow model that shows that the cash flow at the end of a year, right, is actually a static model, right? But when we look at the dynamic model, it describes the behavior of the system through time. So it looks like either a monthly, periodic system, monthly, or weekly, or hourly, or in minutes, or in years, those are how the system behaves, within time or with time. Like for instance, you have a shovel and you have a truck. A truck moves to where the shovel is and the truck is loaded. It is in relation with events and activities within a particular time, let's say in a shift, right? Or you have a typical surveying system where you want to go to the field before they drill, you mark up the areas, you give direction to the drilling operators. They know each point or each location they are drilling. After drilling, they load with explosives, they blast the area, you come back and you evaluate the movement of the blasting material through your geometrical, analysis, right? So you see that your activities are spanning through time by guiding them from beginning to the end, and that is the form of what we say dynamic simulation models, right? So we can simulate that. Then we also have the discrete or continuous or combined discrete continuous simulation models. So what this model means is that they refer to a classified form of models, right, that represents states of change of a particular system, right? State of change of a particular system. So if the change is occurring in isolation, let's say at a particular point, it changes certainty, then we say that it's a discrete, simulation model, right? So it describes the changes in the status of a system at an isolated point in time, right? Then the continuous looks at changes within a continuous flow or phenomenon, right? A continuous flow of phenomenon. Like for instance, the continuous models normally consist of algebraic or differential or difference equations, And then we can also have the combined simulation model where some part of the system behaves discretely and others too behaves in a continuous manner, right? So the simulation process is actually um, shows how simulation modeling, right, is achieved, right, or is conducted to us to be able to assist in making the right decision, right, in solving the problem. So when you see the simulation process, it's just talking about the modeling process in simulation, right, how it's conducted. So over the years, we've realized that for us to simulate a particular system, we have to firstly define the problem. The problem includes clearly defining the goals of the study. What do we want to do? What are the system definitions, right? Identifying the system variables, their interrelationships, and also the various performance criteria, the decision rules. What can we use to say that we are actually modeling the system, right? Then we create a conceptual model framework, right? Or conceptual model formulation, right? So this involves developing a preliminary model, a small model, that we can either see all the various problems, we can see all the various systems, like the various variables and their relationships, usually they are like block diagram or any, you know, um, initial codes that are working, just to represent all the components, the variables, and their relationships in the system. So when that is done and we get grips or we understand that small conceptual model, then we create what we call an experimental design. We don't go straight to the entire experimental design. We just look at a preliminary, experimental design, which involves the selection of the various measures of effectiveness, the factors to vary, the levels of factors to vary, the quantity of the factors that we are dealing with. Are they internal factors, external factors? So we have all these things, designed experimentally, right? Then we now gather our inputs. We gather the kind of inputs that is required in terms of input that can define the objectives, that can define the measurements of the effectiveness of the system, the factors, the data needed for the selection, or sorry, for the study, right? They are identified and they are collected. Then we look at translation of the model, right? Where we code the model in a suitable simulation language, right? So any language of your choice, we begin to then code them. Then after coding, we verify and we validate. So initially, we have to verify using some few data sets from existing world, right? And see whether it's making sense. Like for instance, if I increase the revenue, am I getting more net present value? If I increase if I increase the cost of a particular component, is it affecting the revenue? So if you see the dynamics, because we know that cost will reduce revenue, right? So if your cost is increasing, I should see my revenue decreasing. But if you are not seeing that, then it means that you cannot you have not verified the model well, or your model, the codes may not be working well, right? Very important here. May not be working well, and therefore you cannot, and therefore you cannot validate the model, right? So we usually also validate the model using real data sets, So if that is done, then we can finalize the experimental design and generate the informed, desired model. Then we can perform our simulation, right, which involves executing the simulation to obtain the results. We do our analysis and interpretation on the results, right, inferences, and then we will say that yes, it's making sense. We are done with the simulation process. So in entirely, that's how the simulation process, works. So we will look at the next subject, which is stochastic simulation. All right, so we will take typical activity and we'll simulate it, stochastically. So usually we'll use what we call the Monte Carlo process. We'll use what we call the Monte Carlo process, right? So the Monte Carlo process is a sampling method, right? It's a sampling method or sampling mathematical technique, right, for selecting numbers randomly, right, from a typical probability distribution. And we normally use that in the selection of a simulation run, right? So the technique actually originated in the World War II, right, and attributed to von Neumann and Holland, who used the technique, as a tool for developing the atomic bomb. So the research involved simulation of probabilistic problems concerned with random neutron diffusion of fissionable material for nuclear shelled devices. So the name Monte Carlo, right, was given because the basic principle is the same as that underlying the gambling devices, like the roulette wheels, the dice, playing cards, because you shuffle in and just remove them randomly, you throw the dice and you get some few numbers popping up randomly, So stochastic, simulation is mainly used, to reproduce the variability of random variables in a particular system. So the system is noted to be, randomly generated, right? So they have some variability. So stochastic simulation helps us to be able to reproduce the variability in the system. So the process involve the use of what we call the random process generator. So what is the random process generator? Right, so the random process generator is usually just a system that involves the use of um, a particular medium to select or predict any particular value based on our understanding of how the distribution of some known values related to that, are produced. And we'll look at some few examples and we'll be able to understand what we mean by random process generator. So this is a typical example. So it's a demand per day for a particular product, So we're seeing that the demand is seen to follow the discrete random variable or the discrete discrete. So it's a discrete random variable. The demand is a discrete random variable and is defined by the probability distribution as follows. Like for instance, the probability that it will be 0.2, the demand is 14. The probability that is 0.4, the demand is 15. 0.2, the demand is 16. 0.1, the demand is 17. 0.1, the demand is 18, right? So for us to be able to, create a random process generator, right, to the cumulative distribution function will be used to generate values of the random variables, right? So let's construct this. Let's look at these examples um, in our whiteboard. So let's switch to the whiteboard and let's see how we can generate some random variables, can generate some random numbers. Yeah. Okay, so on this whiteboard here, we can then look at um, how we can use a random process generator, to be able to determine the daily demands, right? So we need to create a cumulative distribution. So the problem itself is a daily demand, called X, a daily demand called X, and there is a probability daily demand. So let me do this so that in case I want to call X, then we have the probability of the demand, right? So assuming we are to collect the data from the beginning, then we can find the probability that there will be a demand of 14, and that will be 0.2. There will be a demand of 15, and that will be 0.4. Demand of 16, 0.2. Demand of 17, 0.1, and demand of 18, 0.1. So here we find the cumulative distribution here. So the cumulative distribution, right, is actually the probability here. Then 0.4 plus that will be 0.6, 0.6 plus 0.2 is 0.8, 0.8 plus 0.1 is that, and that. So that is the typical, so this is the cumulative distribution, right? So you can see that from here, we can actually graph this. We can graph the cumulative distribution, which is the fx. So, which is the fx against the daily demand, which is x, right? Then we can plot 14 and the distribution. So assuming we are starting from 13 here, so I have 14, I have 15, 16, 17, 18 here, right? Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right, so we have this. So we have that, so we can plot 14 and 0.2, which is here. Then we can plot 15 and 0.6, which is somewhere here. 16 and 0.8. We have it here, 17 and 0.9, somewhere there, and 18 and 1. Right, so if you are to look at the probability, the distribution, so it will be in the form of that. Yeah, so at least we have this, right? So we'll be able to, in future, so when we have developed this cumulative distribution function, right, for this x, right, for this demand, right, then we'll be able to, determine which range a typical random falls, right? So, for example, if we have a random variable or a random number of, let's say, 0.6, 0.76, then we'll say that based on that random number, right? Based on that random number, let's say it's within, let me change the color here, right? It's going to hit that and it's going to give us a demand of 16, right? So what this means is that this random number is falling between 0.6, right, and 0.8. And 0.6, 0.8 corresponds to a daily demand of 16, right? So we can see that based on a random number of 0.76, we are able to determine the daily demand, right? So the process of using the Monte Carlo technique to generate the random variable can be demonstrated. So let's say that we have a random number table, right? So random numbers, we'll look at how they are generated, but assuming we have a series of random numbers, right? And let's say the random numbers are let's put some random numbers here, right? Depending on how they are generated, but assuming we have 39, we have 73, we have 72, 75, 37 to 87, right? So we have some few random numbers like that. Right. So because all the random numbers, the maximum are 2-digit numbers, right? So they are 2-digit numbers. So then we need to divide it by 100, right, to be able to get a number between 0 and 1. So it will be 0.39, 0.73, 0.72, 0.75 in that order. Right. So then we'll begin to pick the random numbers sequentially from the first number up to, so we can say that we'll be able to develop a typical demand period, right? A typical demand period, and say that if we need the demand, and so demand period, and we have a random number which will be taken from the distribution function. Then we have what will be the corresponding demand, which is the X, right? So assuming we are generating the first 5 demands, so what will be the first 5 demands, right? So the Monte Carlo technique is being used to generate the first 5 demands. So the first 5 demands, the first one based on the random numbers we have. So let's assume that these are the random numbers. We shall see how we generate random numbers even in Excel or manually, right? So the first one is 39 or 0.39. So we will come here and we'll read 0.39 from the graph, from the cumulative distribution function. So 0.39 is somewhere here, right? And that is hitting 15, right? That is hitting 15. So it means that for 0.39, the demand is 15, right? Then let's look at the next one is 0.73. So for 0.73, we have it somewhere here. The corresponding demand is 16. So 0.73, the corresponding demand is 16. The next one, 0.72. 0.72, we can trace that also here. And that means that 0.72 will also give us a demand of 16. 0.75. So 0.75. So if you know how to code using computers, as the simulation process we said, we code it, right? So you can code, then we'll pick the random number, then it will select the particular demand. This is very easy, right? So 0.75. We also had that one to be 16. So the fifth is 0.37, right? 0.37. So 0.37 is somewhere here. It's 15. 0.37 is 15. So let's say the sixth one, which is 2, 0.02. 2. So 0.02 is somewhere here. That is 14. Right, that is 14. So 0.02 is 14. Remember, the 0.02 is coming from 2 divided by 100, which is 0.02. So at least we can see that we are able to generate the demand based on random process generator, right? Based on the Monte Carlo technique. So if assuming you want to find, let's say, what's the average demand here, right? What's the average demand here? Then that will be 15, 16, 16, 16. That is 30. Okay, let me go this way. 16, 16, 16, 19. Right, so it will be 19 divided by 6, right? 19 divided by 6, and this will be, sorry, 92 divided by 6, 92 divided by 6, and that will be 15.3. So the average demand will actually be 15.3, right? So this is how the random process generator works. That is using the Monte Carlo technique, All right, so we shall look at another example where we are actually going to simulate a particular queuing system, right? We are going to simulate a particular queuing system. Okay, so in a typical environment, the typical mining environment, right? The typical mining environment, right? So you may have a system where a truck must move, to a loader or a shovel, and the shovel will then load sand or gravels or rock materials into the bucket of the truck, So it's something like that, something like that. And you have the buckets, then you have the shovel, which is sitting somewhere there, Yeah. So the shovel sitting somewhere there. So the truck comes in, and is able to maneuver, turn around, loaded, right? So there could be one truck here, right? There could be one truck, right? There could be another, a second truck, which is also coming in here, coming from this side, right? So it's also coming up and it's also coming to be loaded. So as soon as one truck comes, another truck follows, right? The first truck is being loaded. Number one is being loaded. Number two will have to wait, right? And if a third truck comes, it has to form a queue, You have to form a queue, especially if one is still being loaded. So that's a typical example that we want to look at. So let's see the kind of data that we have collected, or the input data that we have so far collected. Okay, so we have this simple problem here, right? So we have an arrival time or arrival interval for a particular queuing system. So the time that the trucks come, and we also have the loading time, right? So when the trucks come, we have collected the data and realize that we have arrival time 1, 2, and 3, and we have 1, 2, and 3. Then we have the probability on the data, right? So the cumulative function for this will be generated at 0.3. 0.3 plus 0.5 will be 0.8. Then we have that. Right, so what will be the random number range for the first one? So the random number range will be from 0 to 0.29. We just want 2 decimal places. You can go 3, that's fine. Then we also have from 0.30 to 0.79, then 0.80 to 0.99. So that is the random number range. It means that that's where, if we are to use the Monte Carlo simulation technique, right, that's where the random number will be identified and chosen from, and then we find the corresponding arrival time. So we can look at the loading time. Now, when the trucks arrives and is being loaded, right, what's the probability that it will be loaded in 2 minutes, in 3 minutes, or in 4 minutes? So we have the various probabilities here. So you can consequently look at the probability function and the cumulative function probability, and that will be 0.30, then 0.60, then plus 0.4 will be 1.00. All right, so the range will be from 0 to 0.29, from 0.30 to 0.59, then from 0.60 to 0.99. All right, so then we have this table. So our first input data was, we only knew the arrival interval and we only knew the loading time, and we have used that to develop the probabilities, and then the cumulative probability function, and then the random number. All right, so assuming now we want to, simulate the next, we want to simulate a system and see both the arrival time or the arrival interval using the arrival interval and the loading time, which have been generated. So we want to look at the next track, when the next track will arrive, and if the next track arrives, how long will it take to be loaded? How long will it take for it to be in the system? Will the track be queuing, or it will just be loaded right away, or it will just wait a while before it just gets loaded? So we shall develop another table that will go through the particular system. So let's say that we are looking at the first 5 trucks that would arrive and get loaded. We are looking at the first 5 that will arrive and get loaded. So let's develop the table now. So we have this system built up in terms of, we want to know the first truck, which is arriving, the second truck, third truck, which is arriving, the fourth one, and the fifth one, right? So what we know from our table is the arrival interval, the loading time. All right, the arrival interval, the loading time. So we will begin with that first. However, we will need to find some random numbers. So let's use our normal random numbers that we generated, that we have here, right? So I want a place to put my random numbers. Okay, great. So I can put it on top here. So let's use green color for our random numbers. So we have 39. So this the number distribution random or numbers, random number generated from normal distribution. Now we'll look at how it's generated. So let's assume we have these random numbers. We didn't generate them, but we use a particular function to generate it. So that is fine. So we have these random numbers here, well laid out, right? So then we'll take them one by one. So what we'll do is that we'll look at the first random number during arrival. So the arrival, so usually there wouldn't be any random number for the arrival time because there is no interval. The first system will start when the track is being loaded. So therefore, the arrival clock will be 0, and the start loading will also be 0. It wouldn't wait, queuing, then there is no queue, right? So the first number will be the R2, the random number 2, which is 39, and that is 0.39. So what will be the corresponding loading time for 0.39? So we'll come here, loading time 0.39 is within this area, and that is 3. So it means that the loading time is going to take 3 minutes to load this first truck that comes, right? And what time will it depart? It will actually depart when it has been completed, when loading is completed. So that means that it will depart in 3 minutes, and that means that the truck came and spent only 3 minutes in the system, right? So let's look at, so the next random number will be 73 divided by 100 is 0.73. So arrival time, what will be the simulated arrival time? So we'll come here, 0.73 is 2 minutes. So it's found here. That's 0.73, and the corresponding time is 2 minutes. So we'll come here and we'll select, we'll write 2 as the arrival time. 2 as the arrival time, right? So we can hold on with generating all this. I would like to do this first. The next number is 72, which is 0.72, and that will be the loading time. So 0.72, the loading time is corresponding to 4. So I'll put my 4 here. I won't continue. I want to populate all this before I calculate that these are just mathematics, right? So it's 75, so 0.75, and 0.75 for the arrival will be 2. So that will also be 2. The next one will be 37. The next random number 37, so 0.37. And what will be the loading time? The loading time will be 3. Then for the fourth track, we have 2. So 0.02. So 0.02, I go to the arrival time, and I have it here, which is 1 minute. So the next track will arrive in 1 minute. That's what it means. Then the next one is 87, which is 0.87. So what will be the loading time? 87 is 4. So it's going to take 4 to be loaded. Then the last track, which is the 5th track, is 98. So it will arrive 0.98 with a random number 0.98. And I'll just pick this to be 3, which is here, 3. And we have 1. So 1 will be 0.01. And the loading time is here, which is 2. So that will be 2. All right, so now let's complete this mathematics. This is just mathematics. So the second track comes in at the time 2, right? So by the time it comes in, the arrival 2, the arrival clock will be 2, because already 0 was in the system, so it will be 2. Then when will it be loaded? It will be loaded after the first track is gone, and therefore it will be loaded at the time 3, when the first track, which is 3, when the first track departs from the system in 3 minutes, right? So that means that as soon as it arrived in 2 minutes and get loaded in 3 minutes, it means that it has waited for 1 minute, right? Was there any track before it came so that it will queue? No, it didn't queue, it was just waiting. So queuing is when you have a track which is being loaded, one track is waiting, then the next track will come to queue. All right, so loading is being loaded at 4 minutes. So we start loading at the time 3, and the loading is going to take 4 minutes. So it means that 4 plus 3 will be 7. So it's going to depart on the 7th time, right? Or at the 7th minute. So it means that it has spent how many minutes? It arrived at the clock 2 and departs 7. So therefore it has spent 5 minutes in the system. Let's look at the third track. The third track arrived also 2 minutes after the third track arrived 2 minutes after the second track. So that means that the clock will be 4 by then, right? When can we load the third track? We can load the third track when the second track is gone. And the second track will be gone in the 7th minute. So it means that we can start loading in the 7th minute. Will it come to wait? And what will be the waiting time? Yes, it's going to wait for, it comes in clock 4 and we start loading it at 7. So it's going to wait for 7 minus 4, which is 3. Will it be queuing? No, because as soon as it came, 1 was already left and 2 was being loaded. So it was waiting. So it means that there is no queue length. Then we ask ourselves here, when we are loading, it's going to take 3 minutes to get loaded. So when can it leave? It can only leave after we start loading, 7 minutes, 3 minutes. So it can only leave in 10 minutes. Then what time has he spent? How much time has he spent in the system? It will leave in 10 minutes. It arrived at the fourth minute. So therefore it has spent 6 minutes in the system. Let's look at the fourth track. The fourth track arrives 1 minute. When he arrived, the clock was 4 for the third track, right? So he's going to add the 1 minute to the clock, which will be 5. Then we'll start loading it when track 3 is gone. And track 3 will be gone when the time is 10. And therefore, we'll start loading it at 10. That means that if it arrives at 5, I will start loading at 10. Then it's going to wait for 5 minutes, right? It's going to wait for 5 minutes. Now, at the 5 minutes, will there be queuing? Yes, because in the 5th minute, right, we have the shovel 1 is gone, but shovel 2 is being loaded in 7th minute. Meanwhile, in the 5th minute, track 4 has arrived. So it means that when track 4 has arrived or arrived in the 5th minute, track 3 was already waiting. So it means that it's going to queue. It will be the first track to queue. So the queue length will be 1. Then we'll take 4 minutes to load the track. In taking the 4 minutes to load the track means that we'll start loading at 10 and it's going to take 4 minutes. That means that it's going to take 14 minutes before it will depart the system. So how many minutes has it spent in the system? It has actually spent 14. It arrived at arrival clock 5 and depart at 14. So 14 minus 5 is 9. So it has spent 9 minutes in the system. Now let's see the last track. The last track, which is the 5th one, will arrive arrives in 3 minutes. So when it arrived in 3 minutes, the time was already 5. So it means that the time has moved to 8, right? But when can we start loading? We can only start loading when track 4 is gone. And that means that at the 14 minutes, when track 4 is gone, that's when we can load track 5. But we can load track 5, meaning that when it came, it has been waiting. So how long will track 5 wait? So track 5 will have to wait for 14 minus 8 because it arrived in time 8 and we start loading it in time 14. So it's going to be there waiting for 6 minutes, right? Waiting for 6 minutes. So before we start loading, right? Would it be queuing? Yes, of course, because when it arrived in the 8 minutes, track 1 is in 3 minutes, it's gone. Track 2 is in 7 minutes, it just left. Track 3 is being loaded. Track 4 is waiting, so it will be queuing, which will be one length. Only one track will be between 8 track 5 and the loading shovel, right? Only one track will be waiting and he will be queuing. So it's going to take 2 minutes to load that track. So if we start loading at 14, then the 2 minutes will be 60, right? That means that it will depart in 16, we start loading, sorry, it arrives in 8, so 16 minus 8 is 8, and that will be the time in the system. So this is a typical shovel track haulage system, right? That is simulated. So this can go on to, let's say, the 10th track, the 15th track that will be coming for a particular shift, right? And it is the Monte Carlo sampling process, which is used to simulate both the arrival interval and the loading time, right? The loading time. So that's how the Monte Carlo works. So based on this information, we'll be able to deduce certain information out. Like for instance, what is the average waiting time, right? So the average waiting time will just be, so let's say average waiting time, right? Will just be the total waiting in the system, which is 1356, 1356, which is 15, right? 15 divided by 5 tracks. And we can see that's 3. Right. We can see that 3, so that is 15 divided by 5. It's equal to 3. Something like that. We can look at the length of queue, right? The length of queue. So the length of queue, we have average length of queue can be 2 divided by 5, right? So that's just the length of queue, which can be 0.4. Then we can look at the average total time at the shovel. So the average total time at the shovel will actually made up of the time in the system, right? So the time in the system when they came up to get loaded. So that will be 5, 6, 11, okay, 5, 11, 20, 28, 31. So that will be 31 on 5, right? And we'll have 6.5, 6.2. Yeah, we'll have 6.2. All right, so this is how we will do the analysis, and I think this is straightforward. So thanks for being with me. I'll end this lecture here. In the next lecture, we will look at the random numbers, how they are generated, right? Then we'll look at some of the few methods that are available for generating random numbers and generating a random variable with a probability density function. All right, so catch you later in the next lecture. Thank you. Bye.